Yeah, so random elimination microscopy is a technique that is developed here and at Institut Fresnel and LS2N in Nantes. So let's jump right into the subject. We try to see inside the living organisms, and we want to take into account that the organism might be a thick sample, it might be moving, it might be fragile. So there is a lot of trade-off to take into account when you want to image such sample, and we saw this morning on the presentation of Virgil that you might have to develop new setup for that. And one family of technique actually that is used to image inside this kind of sample is structured elimination microscopy. So you have a fluorescence microscope that is limited in resolution due to the diffraction of light. And to improve on this resolution, you can play with the way you illuminate your sample. And actually, you can classify a lot of microscopy technique in this family. You can see STED, you can see Eriscan, all these techniques as structured illumination microscopy. And another one is harmonic SIM, where you project harmonic illumination on your sample, and typically 9 of them. And you acquire 9 images that are all low resolution, but you can combine them to create a super resolved image. However, what can happen is that maybe you want to look deep inside your sample, and it will act as a new optical element in your microscope that you have no control on. So it will distort your illumination. So instead of perfect harmonic illumination, you will have something like that. And this will be quite detrimental to the reconstruction quality of your super resolved image. So you can have a strong artifact in this case. So what we propose instead is to illuminate with random patterns, which we call speckle. It's a type of illumination that naturally arises when you let light propagate in a complex medium. And we will see how we use this kind of movie to create super resolved image. So in this movie, all the fluctuation you see is us changing the pattern in between each frame. So each frame will change the speckle. Okay, so let's do a little bit of math just to understand what's happening. You have this equation that represents your microscope. You have the PSF that is linked to the quality of your microscope. And you have noise and your sample. The sample is what you try to recover. So you try to get a super resolved image of your sample. And finally, the illumination. And in our case, what is particular with our technique is that we consider the illumination to be unknown because we want anything to be able to happen to this, almost anything. What we suppose is just a little bit of information to be known is a statistical information called the covariance. And why do we use this? It's because when you look at speckle, for instance, here you have a real movie acquired of speckles when you change the focal plane. You see the size of the grain and the typical shape of the grain is not changing. So this is what you see when you calculate the autocorrelation. It's an average shape of your grain, of the speckle. And it's not changing with depth, so that's the first thing. But you can also do the same by introducing aberration in your system. If you introduce phase aberration, it's also not changing this typical grain shape. And it's actually exactly what is captured by this covariance. So it's a quite robust knowledge that we have in advance about the illumination that we can use. Okay, we will see how we do that later. And finally, the images. We have really bad quality images, but we combine multiple of them. So if you take one of these images, it's only a few photons per pixel. The fluctuation is what matters to us. And it's what we will use to calculate a super resolved image. And typically, we use between 50 to 200 of these images to create one reconstruction like that. Okay, so we are using the fluctuation of the signal. And this can be encoded in a value called the variance. So you can, for each pixel, calculate a variance image. And you can predict what this variance should be. So you have an equation that's telling you what the variance of your signal should be if you plug the value h, the PSF, your sample, and this famous gamma of I that I was mentioning before. So in this equation, there is no illumination, there is a gamma of I only. And there is a variance due to the noise, which we can estimate from the images also. And this variance, you can compare it. So if you plug a guess of what the sample is inside this equation, you have one image of variance, but you can compare it to a variance that you can calculate from the images. So you have your set of images, and for each pixel, you calculate the variance among the images. And you can compare these two images through a mathematical distance. And typically, your first guess will be quite bad, so the two variances image will be different. But you also have rules to iteratively update your guess, and you have an algorithm now to estimate your sample, because it will converge to something, and you have the best guess you can get. We also have a mathematical proof that in ideal condition, we can solve this equation without ambiguity, and this result is telling us that we can double the resolution of the microscope, like in SIM, for instance. Same kind of resolution improvement, both in terms of lateral increase and also axial. So the optical sectioning will be increased a lot. And this is with unknown illuminations. So that's theory, but then we did quite a broad study of the behavior of this algorithm in simulations, and now it's commonly used in the microscope is used a lot for different biological applications. So here I have one example of a movie where you have a cell migrating. On the left, you have the wide field movie, and on the right, you have the rim reconstructed movie, where you can maybe see, I don't know, from your place, the gain in optical sectioning and in resolution. So typically, we have between 90 to 130 nanometer resolution in X and Y, and 300 in Z. The field of view is not limited to the technique. The speed is between 0.1 to 20 Hertz right now, but I will present it, working on an improvement on this direction. We can do 3D, multicolor, and we have no constraint on the fluorescence labeling. Okay, so now there is papers that start to be published using our technique. So I want to mention a few of them, just as illustrations. So in structural biology, you have here an example on centriole, which was made by a group from Barcelona. They came here to use the microscope. And on the right, you have adhesion in osteoclast, in living osteoclast. You have an example with, again, cell migration, the macrophage, and the podosome. The movie is not to show a multicolor movie. Okay. Where they study the force of the podosomes. And it's not changing the slide anymore. Okay, no, it's changing again. Okay, and finally, an example with a study of chromatin interactions, DNA and damage repair, where we have there's a paper published by Gail Legub's team on Nature with a lot of rim images where they discovered a new compartment on the chromatin. Yeah. So that's all good news for rim, but now let's talk about limitation and what we are doing to work on this limitation. The number of images we need. That's a price to pay right now. Why? It's because we calculate this variance, and depending on the number of images you take, the quality of this variance image will be good or bad. If you take only 16 of, this is simulations, that's the sample I use for the simulation, and if you take only 16 images, it will be quite bad. You need at least more than 50 images to have something meaningful. And that's something we are working on to improve. So what we do is we try to look at what a speckle is, what property it follows, and we try to mimic this property, but with adding more control on the way we illuminate. So we have developed new kind of pattern of light. Some are not new actually, but and we have patented this idea so that basically we can create sets of illumination that we can project on the sample, and we will see that we can mimic some property of the speckle while reducing the number of images we need. So for instance, I can show you the same simulation just as before with a random speckle, and now with this kind of pseudo-random illuminations. And you can see that even with just 7 illumination, you already have a quite good variance image. Okay, but that's good, but now we have added control on our illumination. So we don't want to rely on this full control. So what happens if we look in depth? Well, this illumination will be changed by aberrations. And I made a small simulation to explain why we can still process this kind of images. So in depth, your illumination will slowly become a speckle again. So first thing, I've looked at the statistical property I was mentioning, so the typical grain shape of the speckle. And actually, we have to choose this illumination so that it's similar. So for all this kind of illumination, this one we have perfect control, this one is totally random. It's always the same average grain size. To speak, yeah. So you can. This is the input of the algorithm. So you can use always the same algorithm, whatever the illumination you have. And now you can do reconstruction. If you have full control of your illumination, the reconstruction works all the time. So on the right here is when you have full control. If you use 12 illumination or 480, it's always working. On the left, it's when you have totally random illumination, so no more control of your illumination. It's not working at all with 12 illumination, but you recover the rim performances. So you need a few hundred of illumination to recover these performances. And you have all the performance in between. And what we think is, in biology, most of the time, you won't be with a total random illumination. Most likely you will have some small distortion. So what we hope is that for most application, we stay close to the fully controlled illumination, so we can reduce a lot the number of images we need. And here I have an example with a real data set on chromatin in the nucleus, where we show that you have this reconstruction for 200 speckles, this one for 32 speckles, which is even better than the 200 one, compared to the 32 speckles. And we start to apply this with a fast-moving sample. So you have a live imaging of chromatin again, and here it's mini filament of myosin. So we are currently evaluating how fast we can go on this kind of applications. So all I have presented until now was on a normal fluorescence microscope. But this kind of technique can also be applied to different kind of microscopes. For instance, you can apply this to TIFF microscope. It was also applied to CARS microscope in Fresnel at Marseille. This isn't testing because it's a label-free technique, so it might have also advantages for biology. You can modify your PSF. For instance, you can do extended depth of field. So you can create an elongated PSF so that everything is in focus. So that's nice if you have something moving in Z and you want to keep it in focus. And also you can combine it with expansion microscopy, where you cheat by making your sample bigger. And so here you have a central image with rim compared to an electronic microscope. Okay, I want to leave you with this application, and thank you all for your attention.